Hello there. Daniel and I will present findings for our anchor paper, which focuses on the area around physical layer wireless security. The rapid acceleration of the Internet of Things has increased the need for improved security, especially for wireless systems that are more vulnerable to attacks. This research area aims to replace or improve upon cryptographic methods of applying security. As this is a short presentation and the state of the art is diverse, only a few important sections will be covered. I will cover the literature survey component, going into the exchange of keys, the concept of jamming, and then relating to what our anchor paper aims to achieve. Daniel will follow on with a critical review, describing the strengths and possible weaknesses, and an overall view on the author's research and experimental methodology. Physical layer security has become more popular over the past decade. I mentioned that this area is in direct competition with cryptographic methods, and aims one day to replace it. However, there are several problems. Generating these keys requires a lot of calculations, which makes it infeasible for devices with low computational resources like sensors and actuators. On the other hand, physical layer security is a lightweight approach that just encompasses those methods to take advantage of the randomness experienced in a wireless channel. Either you're aiming to provide a secured channel, perfect secrecy, without the need for encryption, or generating and exchanging keys based on this randomness, and the latter approach will be analyzed in this presentation. It all goes back to the work done like 60 years ago, where the idea of a wiretap model and perfect secrecy was introduced. Assuming discrete, memoryless channels, an eavesdropper would view the transmitted data by, say, the main node Alice through a second channel. In essence, the theory was to increase the level of confusion for the eavesdropper's channel, so as to degrade this channel relative to the main channel. So even if the eavesdropper knows the encoding and decoding scheme at the source and destination, they are kept oblivious to the transmitted data being transmitted, and thus can yield perfect secrecy, where the eavesdropper obtains no data. In the current state of the art, the adversary or eavesdropper is determined to be passive. They can only listen to the wireless channel and not transmit. Thus, active attacks like DDoS and man-in-the-middle attacks, which you may have heard of, don't need to be examined. However, this is one aspect that requires research into the future. The previous idea was in the absence of generating a key, but the following presentation will go in the other direction. There has been established a general protocol, as shown in the image, but papers have examined ways to alter these steps in order to increase the bit rate, which is the rate of key bits generated without compromising the channel to the eavesdropper. The main idea is to exploit the randomness in the channel, which was hinted at earlier. Relative system movements generate signal fluctuations for multipath propagation, known as temporal variation. Two nodes on the same channel can experience the same channel fading or interference, and thus can obtain the same information and use this information to generate a key. And then two nodes at least half a wavelength apart receives uncorrelated signal. So these two nodes can't calculate the same key. Now to some examples in the literature, which I will skim over. One article used a proportional integral derivative probing system with a variable rate to improve the channel probing, adjusting the quantization according to the signal-to-noise ratio of the channel, and to improve key reconciliation, a T-error correcting code, and a protocol involving pre-processing to generate K-code words, which formed a new key at the receiver, was introduced. Before we get into what our anchor paper's novel strategy is, an understanding of cooperative jamming in relay is required. In a traditional sense, jamming is used by an attacker to affect legitimate messages, but in this aspect it is used to degrade the eavesdropper's channel. When combined with using an external friendly node, this can impact the strength of the signal and thus provide more confusion, thus improving security. Friendly nodes choose to sacrifice their own weight in order to transmit a jamming signal to the eavesdropper. These signals can include generic Gaussian noise, specific code words, or specific signals only known at the trusted nodes. Surprisingly, there has been evidence where cooperation with untrusted nodes are beneficial to the secrecy rate. In one example, the authors assumed an untrusted relay node where a positive secrecy rate would result. An eavesdropper R is assumed to be an untrusted relay node, and an external jammer was introduced. Other schemes use relay networks, multiple antennas, where the eavesdropper can be actual relay node or external to the system, as well as schemes for going the external node and subjecting the jamming signal within the system. So, for example, the destination transmits the jamming signal. Our anchor paper suggests a novel system called iGEM, which aims to generate a key in static systems, where there is an absence of channel randomness. In order to generate strong keys, the channel needs to change fast, which is the reason why this research area is becoming more popular, as the real-world scenarios, the ideal scenario, just can't happen. The main way is to introduce artificial noise, in which a message transmitted appears random. So in this, a digital modulation scheme is introduced. A common one is orthogonal frequency domain modulation, and its scheme is shown on the right. The signal design is complex and beyond the scope of this presentation, but the audience is welcome to research it further. In our anchor paper, iGEM is a novel scheme introduced. A salt, a random sequence of bits, and associated OFDM signal are generated at the source. By transmitting the same two OFDM signals, the receiver knows to when to start jamming, and can essentially stitch the unjammed signals to find the original salt, and generate the key. By using a high modulation rate, the adversary doesn't know which signal is the unjammed one, and thus can't determine whether the message with a probability better than random guess. By using a high modulation rate, the adversary doesn't know which signal is the unjammed one, and thus can't determine the message with a probability better than a random guess. Another example which was interesting is a scheme called Smoke Grenade, and it was theoretically found that the key generation rate increases with the increment of the interference power. A trusted external node transmits a jamming signal that contributes to the change of measured values on channel states, which are the parameters that are exploited to generate keys.
The paper proposes key strengths to iGEM that make it a robust solution to physical layer security. A key strength in iGEM is that the receiver will encrypt or jam the signal, as well as decrypt or reconstruct the signal, which departs greatly from modern encryption schemes and lowers the complexity of encryption. Now, the authors also suggest multiple techniques in order to make iGEM location independent to solve the problem of the variance of the jamming power depending on Bob and Eve's location. For the region where the jamming power is too low, iGEM would be extended by using a two-way exchange of salts. Alice will first send a random salt to Bob, and he will jam it to make it unreadable. Once received, Bob will send a new random salt, in which Alice will jam as well. With these two salts, Alice and Bob will XOR them to obtain the new random key. However, regardless of Eve's location, there will exist at least one salt where the jamming power is high enough so that she cannot decode it, and hence cannot generate the same key. Now, for the region where the jamming power is too high, this is problematic as Eve will be able to identify the jam samples. To address this problem, Alice and Bob will instead transmit multiple salts in each direction at different power levels. The jammer will jam each salt and its repetition using a different power level. Once all salts are transmitted in each direction and acknowledged, Alice and Bob will XOR all acknowledged salts to generate the same key. However, there will be at least one salt for which the power ratio will correctly jam the signal in which the jam samples are unidentifiable to Eve. Hence, she will not have all salts to generate the same key. Within this paper, they suggest that having an appropriate number of salts transmitted is key in order to decrease the amount of information Eve can obtain. This is greatly dependent on the modulation scheme chosen. Now, how can iJam make sure Eve cannot get any information from the signals? The iJam authors suggest increasing the bit error rate, or BER, to be close to 50%. A BER of 50% would indicate Eve gets no more information than she would from a random guess. So instead of transmitting just one salt for each power level, the transmitter sends M salts. The final salt for each power level is constructed by XORing these M salts. The probability that the ith bit is uncorrupted in all M salts decreases exponentially with the number of salts sent on each power level. This exponential trend can be used to increase the BER at the eavesdropper to about 50%. Now, the authors evaluated iJam using an indoor testbed with 20 nodes in line of sight and non-line of sight locations. They were able to find the following. For all modulation schemes, iJam could magnify the BER to 50% by picking appropriate number of salts to transmit over each power level. For 16 QAM and 64 QAM, about 15 to 30 salts were required, and for 4 QAM, about 90 salts were needed to achieve a BER of 50%. iJam was also able to generate a 512-bit secret key in 28 to 168 milliseconds. This corresponded to a secrecy rate of 3 to 18 kilobytes per second. However, from critical analysis, you can identify multiple weaknesses not explored within the paper. The paper assumes that packets are sent and received within less than 1 millisecond. However, packet transmission time depends greatly on the packet size and the bitrate of the network. It also disregarded processing time in order to decode packets. Hence, in essence, more experimentation would be needed to prove these performance times as accurate in real-life environments. It also becomes apparent that iJam is vulnerable to tampering from adversaries. iJam dictates Alice and Bob requires a minimum amount of salts to be received and acknowledged. However, no protocol is put into place to prevent infinitely sending salts if a malicious adversary is present. Hence, some threshold could be employed to indicate when to stop iJam when there is a possibility of a malicious attacker. Another issue not explored is the vulnerability of using repeated salts. With more devices needing wireless connection, this means more salts are required using the iJam system. No mechanism is put into place to ensure no repeated salts are used in order to prevent attacks similar to replay attacks. An attacker may also be able to use statistical analysis in order to match signals with known decrypted ones. Overall, the authors of our research paper present the iJam system that explore new and innovative techniques to ensure physical layer security to communicate secret bits in the presence of an eavesdropper without encryption. Thank you for watching.